Today I'll be speaking about a large deviation principle for block models. This is joint work with Christian and Schuberta, who are of course here, as well as Jennifer Chase and Samantha Petty. Right. So our work fits in the area of large deviations for random graphs. To motivate this area, consider GNP, the Erdős-Rényi random graph, and let T sub n denote the number of triangles in this graph. Let's fix delta to be positive, and let's consider the probability that the number of triangles exceeds the expected number of triangles by like a 1 plus delta multiplicative factor. Of course, this is an unlikely event, and one question we could ask is how unlikely is that? So that would be like a typical large deviation type question. But in addition, we might also be interested in the structure of the graph conditioned on this unlikely event of having, let's say, twice the expected number of triangles. In other words, what is responsible for an elevated triangle count? Is it just that there are more edges spread throughout the graph? Or maybe some small dense graphs like cliques are responsible for generating this large number of triangles? That's a phenomenon called localization. Why is this interesting from a mathematical standpoint? Well, if we let A to be the adjacency matrix, then the number of triangles can be expressed as a sum of products of 3 entries in the adjacency matrix. And that's a nonlinear function of these independent random variables in the adjacency matrix. And so standard large deviation theory simply doesn't apply to this setting. And as I've mentioned, we expect some kind of unusual phenomena to arise, like localization. The problem of studying triangle counts specifically in the upper tail has been referred to as the infamous upper tail problem, and it has inspired many new ideas in probabilistic combinatorics. Today's focus will be on large deviations in dense graphs, though there's been really interesting work, though using very different techniques in the sparse setting. So the key idea for the Erdős-Rényi case, which was done in prior work, is to represent an Erdős-Rényi random graph as a graphon. This was done by both Chatterjee and Varadhan, Lubetzky and Zhao, and others. The way this is done, as has been seen in other talks, is by constructing what's called the empirical graphon, where we kind of divide up the 0, 1 square into n squared cells. And if I and j form an edge, then the ij cell takes value 1, otherwise it takes value 0. Here pictorially I've represented 1s by black and 0 by white. And so if we increase n and generate these empirical graphons, they'll get more and more gray until finally they really look like this gray region. This would be a typical realization if you were to take n very large. So like if the parameter of the Erdős-Rényi is 1/3, then this gray region would represent the value 1/3 in a typical realization. But what we're interested in is atypical realizations conditioned, let's say, on having twice as many triangles as expected. So because we can represent an Erdős-Rényi graph as an empirical graphon, we can naturally describe large deviations through the language of graphons. So this theory of graphon topology has been developed by a line of work, including these individuals. As some of this has been mentioned before, so I'll go relatively quickly, but a graphon is any measurable function from the 0, 1 square to the interval 0 and 1 that is symmetric. Here I'll let the space W collect all graphons. 2 graphons can be compared by their cut distance, which is this expression. They can also be compared by their cut metric, which is their cut distance, but allowing one of the graphons to be kind of scrambled. More precisely, if we let M be the set of bijective measure preserving transformations, and this notation G phi kind of transposes each coordinate. So if we allow this certain kind of restricted scrambling, then the cut metric is so defined. The cut metric induces an equivalence relation. Let's say F and G are equivalent if their cut metric value is 0. And then we'll let W tilde be the set of these equivalence classes, where the cut metric value of two equivalence classes is computed according to their representative elements. And one well-known result is this space W tilde equipped with a cut metric as a compact metric space. All right, because we're interested in, let's say, subgraph counts, we introduce our work uses the homomorphism density. So for a fixed subgraph H, let's say a triangle, the homomorphism density of H in a graphon F is this integral where the integrand is a product, where like the ij kind of range over the edges of the subgraph. And like, why does this kind of match up with our notion of subgraph counts in graphs? Well, if we let Fg to be the empirical graphon associated with a graph G, then a rescaled version of what we already saw to be the number of triangles in G is actually the homomorphism density of triangles in the empirical graphon. So there's this like relationship that kind of matches up with what we're trying to count in actual graphs versus in graphons. And there's like a related definition of homomorphism density with respect to equivalence classes, not just graphons themselves. And it's also like a known fact is that for any fixed graph H, this map from equivalence classes to homomorphism densities is continuous under the cut topology. All right, so let's now go back and consider the random graph GNP for a fixed P between 0 and 1. And so like, as I've alluded, this empirical graphon induces a distribution on W tilde equipped with a cut metric. And so that naturally induces a sequence of probability measures denoted by this PNP with a tilde, where N and P are just recording the parameters of the graph. And so what prior work has done is to derive an LGP for graphs in terms of this P tilde. To state the prior work, it's in terms of a relative entropy. So given a kind of a base graphon W naught, which is just a graphon which takes value P, then the relative entropy of some other graphon F with respect to the base graphon is this integral of relative entropies, where this function H sub P is the usual relative entropy. We integrate over the whole square, and we kind of compare the value f, x, y to P. What Chatterjee and Varadhan showed that for any fixed P, this sequence of probability measures. Any question?
Yeah. So in your previous formula, you have a W naught, right? You're assuming that is the constant P.
Yes, I should have written that.
Otherwise, your subscript should be W 0 x y, right?
Yeah. Yes, agreed. But because yes, W naught in this context is the constant value graphon which takes value P. That agreed. That was not specifically written, but that's what I mean. Yeah. So the prior work said for fixed P. The sequence of probability measures satisfies an LGP with speed n squared and the rate function I, which formally means that two things. So an upper bound and a lower bound, that for any closed set F tilde, when you take the probability of F tilde, take the log and then divide by the speed n squared, the upper bound is the infimum over the H tildes within the closed set. And similarly, for an open set, there's like a kind of corresponding lower bound where taking the relative entropy of an equivalence class, you just choose a representative element in this context. All right, and then in addition to determining probabilities of unlikely events, there's also known results about the typical structure under a rare event. So for a closed set F tilde, we'll let F tilde star be the subset of F tilde where the rate function is minimized. Then that set is non-empty and compact. And moreover, if you condition on GNP kind of being described by the event F tilde, then this GNP is going to be close in cut metric to F tilde star with high probability. That's what this is saying. And so in particular, if this optimal set is actually a singleton, then the conditional distribution under the unlikely conditioning is going to be concentrated at a single point. Let's dive into the upper tail variation problem. So let phi p comma t be the optimal value of the rate function with the constraint of satisfying the required triangle count. If the minimizer of phi is a constant, then that's interpreted as an Erdős-Rényi random graph with a higher edge density. We'll call that symmetry naturally. Sometimes the minimizer will be non-constant. That's called symmetry-breaking. So it's actually very well understood for dense Erdős-Rényi graphs. So here's what's known. If G has parameter P and we condition on an elevated triangle count, let R be the edge probability for which that elevated triangle count is typical. And here is what Lubetzky and Zhao determined. So we'll consider only P and R such that R is bigger than P because this is for the upper tail variational problem. The blue region is the symmetric regime. So if the pair PR falls into the blue region, then conditioned on the unlikely event, the conditional distribution of the graph will mimic G and R. It will have the same distribution as G and R. In the white region, that's the non-symmetric regime. The distribution does not match G and R. It's actually not known what the distribution is, but they're able to rule out G and R. And if you're wondering what this dashed line is, prior work of, I think it was Chatterjee and Varadhan, showed that this region was blue, but didn't completely fill in the box. So what is left to know in this context? There's no phase diagram known, at least not to my knowledge, for non-regular graphs. I've already mentioned we don't know what happens in the symmetry breaking regime. What about other functionals? Not necessarily subgraph counts. A lot really remains unknown in the Erdős-Rényi context. Our focus was actually on large deviations outside of the Erdős-Rényi case. Of course, random graphs with inhomogeneities or various constraints are common. Here are a few such models. And so large deviations in this context are of natural interest, and we expect new phenomena to occur. Our focus is on block models. We construct a graphon with k blocks of equal length. The edge probabilities for these blocks are specified by PAB, where A and B both range from 1 to k and are symmetric. Our base graphon, which is kind of the analog of the constant valued graphon from the Erdős-Rényi case, it'll take value PAB on the AB block. The random graph that we consider, it has kn vertices, where n vertices are belong to each block. We add edges independently with certain probabilities. So like we add edge ij with this given probability. I think it's easier to explain a different way. So if vertex I is in block A and vertex J is in block B, then I and J are connected by an edge with probability PAB. So in other words, we kind of look up the block membership and then decide with what probability we connect a given pair of vertices.
So just to clarify, the base graph has all communities the same. Is that what that edge means?
They're all, yeah, so that I was going to come to that. So yes, our model has like blocks of the same length, but that doesn't mean we can't accommodate other kinds of block models. So yes, repeated values are allowed. And so that means we can actually accommodate any rational length blocks. And so there's kind of this relationship between our sampled graph and of course its empirical graphon representation. And so the distribution of graphs naturally induces a distribution just as in the Erdős-Rényi case. So it's very much analogous as might be expected. And so as in the Erdős-Rényi case, our goal is to derive an LDP for graphs in terms of this P tilde. There is a subtlety that arises when working with block models. Namely, some blocks can be equal to 0 or 1. And at first that might sound like a strange edge case, but you might just consider, let's say, the bipartite Erdős-Rényi case. And that leads to issues when calculating relative entropies of a graph on F compared to the base graph on W naught. And so like in particular, if like PAB is a 0 or 1, but a graph on F does not agree, then that like relative entropy is going to shoot up to infinity. And of course, that issue does not arise in the Erdős-Rényi context because like the only interesting values of P are strictly between 0 and 1. And our solution then is to restrict the support appropriately for the LGP. So we'll let omega denote the pairs x, y, such that the base graphon is strictly between 0 and 1. And we'll let W with a subscript of omega be the graphons that kind of agree with the base graphon. And kind of going along that same direction, W tilde with an omega is the set of equivalence classes that agree in an appropriate sense with the base graphon. And so like certain like desirable analytic properties are still preserved when we like make this restriction to omega. So like what should our rate function be? Let's recall what it was in the Erdős-Rényi setting. It was this function I, where, okay, again, here we're assuming that the base graph on W naught is constant and takes value P. So a first guess would be to just replace P with the W naught evaluated at XY. Okay, that doesn't work because it's not well defined on this like equivalence class, right? Because kind of depends, like if you take two different representatives of a given equivalence class, they'll have different I values. So like already we see there are problems, and also we need to ensure lower semi-continuity of the rate function. And so our rate function that we proposed was for given like equivalence class F, we'll take an eta ball around F and look at all graphons H, which are close to F tilde, and then evaluate their relative entropy as like using this definition and infinity otherwise. Okay, that looks kind of complicated. Others have since simplified this rate function. So just kind of repeating this definition, what we showed is that the sequence of probability measures satisfies an LGP with speed n squared and this rate function. But yeah.
Under the cut metrics under all.
Oh yeah, you're right. Cut metric ball. Yeah. And yeah, since then, Grebic and Prokurko simplified the rate function. It turns out you don't need to take an eta ball. You just consider only H's that have cut metric value equal to 0 compared to F tilde. This had been shown, although it seems like it was later, by markering under an additional condition. And like we were interested in applying our LGP to homomorphism densities because that corresponds to subgraph densities in graphs. So let's fix a graph H, for example, that has to be deregular. So like let's say triangle, and let's let T max kind of be the maximal attainable value of the homomorphism density. And for T, which is like attainable but strictly lower, let phi be kind of the best rate function value subject to respecting the constraint. We showed that yeah, the probability of like achieving that value, if you take the log and appropriately scale, then that equals the negative of this like optimal value. And also like looking into the structure of the optimal solution, if we let F tilde star be the subset where this rate function is minimized, that's non-empty and compact, and moreover, there's a concentration property as we saw before in the Erdős-Rényi case. And in particular, if the optimizing set is a singleton, that means that the conditional distribution is going to be concentrated at a single point. And let's talk about symmetry versus symmetry breaking. So a natural question would be, do the minimizers of the variational problem have the same block structure as the base graphon? Well, what we showed was for a fixed deregular graph H, if T, the like demanded density, is larger than kind of what's expected under the base graphon, but only by a little bit, then the minimizer of the variational problem is unique and symmetric. Also, if t is very close to the maximal attainable value, then the minimizer is also unique and symmetric. So there are these two extremes where we see a symmetric solution. And regarding symmetry breaking, in that regime, or like just the definition is that the optimizing graphon has a different structure from the base graphon. We are able to establish symmetry breaking for only certain special cases of a base graphon. So then in these examples, combining with the symmetric results, that establishes what's called a reentrant phase transition, because you go from symmetric to symmetry breaking to symmetric as a parameter is changed. We do know the specific boundary for symmetry versus symmetry breaking for bipartite Erdős-Rényi graphs. So that's kind of complementary to the existing results of Lubetzky and Zhao, who also identified this boundary in the Erdős-Rényi case. I'll sketch some of the proof ideas. So for the LDP context, yeah, I mean, the lower bound was like relatively straightforward, so I'll focus on the upper bound. The prior work of Chatterjee and Varadhan really relies on the fact that an Erdős-Rényi random graph remains invariant in law under vertex permutation. So if you were to like change the labels of the vertices, the likelihood of the graph remains unchanged. But that's not true in the stochastic block model, because the probability of an edge depends on the group memberships of the vertices involved. We took a two-step approach in deriving the upper bound. First, we applied Symmetry's regularity lemma that allowed us to construct a Symmetry net of block graphons. And then we could cover an event by a finite union of open balls centered on the elements of this net. And that meant that that it was sufficient to characterize the limiting probability of each open ball, which kind of reduced the problem. Next, we applied a method of types style argument, kind of reminiscent of proof of the Sanov's theorem. Sorry? Sanov's theorem? Largely. Oh, yeah. I'll say like in this context, if that's okay. So yeah, so the meaning of the word type is kind of the origin of each vertex. So each vertex is a member of some block. We consider the block membership the type of the vertex. And because its type influences how likely it forms edges with vertices of other types, when we go to compute relative entropies and probabilities of certain events happening, we compare the base graphon to the empirical graphon according to how like the types were aligned, roughly speaking. Right. Now I'll describe some proof ideas in the symmetric regime. So here we fix P and some D greater than or equal to 2. The purpose of all this construction is for establishing the symmetric regime for D regular graphs. So like for the triangle case, D would be equal to 2. Then we define psi sub P as this function, which is kind of like related to our a relative entropy H sub P. So if like for the triangle case, we would just take the square root of X over here. And then we let psi hat denote the convex minorant of psi. So this was a notion that was used in the Lubetzky-Zhao paper in order to kind of study the symmetry versus symmetry breaking regimes. And here is an illustration from their paper. So it's kind of it's more like a cartoon. It's not to scale necessarily, but it's an illustration of the function X, which is mapped to H sub P of X to the 1 minus 1 over gamma, where like in this context, gamma would be an integer representing the degree of the graph. And it has this form where like if P in their context was the like Erdős-Rényi parameter, then it has this like visual behavior with like certain inflection points and such. And kind of this red line tells you kind of how the convex minorant behaves around psi. So the convex minorant would be this function that kind of makes a departure by following the red dashed line. In order to keep going with the symmetric regime proof, we introduced a certain representation of Graphon. So if over here we have a Graphon F, which has this block structure, we kind of introduce this zooming in idea, where let's say to zoom in on the 1-2 block over here. So first row, second column, a given point here, which is let's say halfway through the block, going right and a quarter of the way going down, would be mapped to the point that is at 1/2, 1/4. And then we'll also just introducing more notation. The D norm of a Graphon is this. Then our guarantee for the symmetric regime is through what we refer to as a convex minorant condition, inspired by the work of Lubetzky and Zhao. Let W naught be the base Graphon, where W naught is described by some Pij's. And let F be a Graphon that's described by these Fij's. So this would be an example of an F that can be kind of written in terms of, let's say, F11, F12, et cetera, et cetera. And we say that F satisfies the epsilon neighborhood minorant condition if for all ij such that Pij is strictly between 0 and 1, whenever x is in an epsilon neighborhood of the D norm of Fij raised to the D, then the function psi and its convex minorant coincide. So pictorially, here's again the representation of psi. So that'll be the black line, and psi hat would follow the red line. So let's say I and j are such that this D norm is somewhere over here, somewhere kind of safely within the region where the convex minorant and its where psi and its convex minorant coincide. Then the epsilon minorant condition would be satisfied for that pair ij, but it has to be satisfied not just for that ij, but for all of them. So if it holds for all of them, then we say that the epsilon neighborhood minorant condition is satisfied. Our key lemma goes like this. So if W naught is our base Graphon, and F tilde is a minimizer of the variational problem for the homomorphism density for H, which is a deregular graph. Suppose there exists a sequence of Graphons Fn such that first, each Fn satisfies the epsilon neighborhood minorant condition, and the sequence Fn converges in cut metric to F tilde, the minimizer. And the I type rate function of the Fn's converges to the J type rate function of F tilde. Then we can conclude that F tilde matches the block structure of W naught. Now, in terms of intuition for why this convex minorant condition matters, well, that was real. Remember that the results of Lubetzky and Zhao completely characterized the regime, and they went through this type of convex minorant condition. So I think understanding this, I would really go to the Lubetzky and Zhao paper because somehow this is this convex minorant type thing is really what's driving whether or not the Erdős-Rényi case has a symmetric versus non-symmetric solution. Right. Yes.
Do the assumptions automatically imply the minimizer is unique, or is that an additional constraint, which is suppose if tilde is a minimizer?
Yeah, I don't know. So the uniqueness was something else. This you're right. Yeah.
We don't say that, right? We say symmetric if the minimizer has block structure. We don't say it.
We don't need uniqueness.
In the non-symmetric regime, again, we only did this for a couple of special cases. It's just about constructing an example that satisfies two properties. So that's of course non-symmetric, and also whatever the constraint is, like homomorphism density is satisfied, and also the relative entropy has to be strictly lower than whatever it is for the symmetric solution. And yeah, so you get like examples like, okay, so if R is the symmetric value, then you construct graphons that have like slightly larger values, like or in slightly smaller values in different places, and somehow that's going to have like maintain the homomorphism density but decrease the relative entropy. And it's very much on a case-by-case basis. And like one interesting question would be to make this more systematic. Also, we don't claim anything about this being the actual solution. I really doubt that it is. So like really pinpointing what is the correct solution in the non-symmetric regime, I think would be pretty difficult. There have been some subsequent developments since our paper was posted to archive. For example, Dupuy and Medvedev considered, the inhomogeneous LDP, as did we, using a weak convergence method. The variational problem, so I'll mention that. So we focused mainly on subgraph counts, so homomorphism density, but this group of authors considered the spectral radius, and I think maybe this will be I guess this will be mentioned later or talked about later this week. Also, like sample path large deviations have been considered. I guess I've mentioned the work of Grebeck and Pokurko. They simplified the expression for the rate function. They were also able to extend to irrational block lengths. So I mentioned how we can accommodate rational block lengths, but really it was a little bit arbitrary, I guess, that our blocks were of equal size. I'll mention some directions for open problems. Of course, nailing down this precise boundary between the symmetric and non-symmetric regimes, we're very far from that. Of course, what happens in the symmetry breaking phase, that's not even known in the Erdős context, so it'd be interesting to start there, I think. Also, this notion of uniqueness in the symmetry breaking phase, is the optimizer unique? And what about large deviations for non-regular subgraph counts? Even in the Erdős setting, the results are limited to deregular graphs. And that's all I had. Thank you very much for your attention.
Great. Questions?
In stochastic block models, there's basically two types of settings. One where you say deterministically how many vertices there are of each of the different phases. And you could also assume that the types are chosen in an IID manner. I would guess that your results do not extend to that setting.
No, they don't, because unlikely events could then be due to two different reasons, right? You could
one is exponentially more likely than the other, right?
Right. So it could be just because there are like more vertices in the community with higher probability, and that's what's driving the elevated triangle count.
But you're probably going to get a phase separation once where you can get many triangles by changing the type distribution. But at a certain moment, that may no longer be possible. That's going to be exponentially unlikely. And then you're going to have to do something similar to what you're doing.
Right. So it'd be interesting to see, like, as like the demand for triangles changes, what's the right kind of strategy? What's the optimal solution to the variational problem? Is it kind of, making communities
probably
more,
two phases.
It's kind of,
Yeah, that would be my guess.
Interesting.
Yeah.
So,
Already have results consider the random choice of the memberships as well. Okay. They derive the LDP at the scale m and at the scale n squared. Right. Okay.
Thanks. Didn't know that.
Can you just repeat it for the
Oh yeah.
audience?
Yeah, so there are results by Grebeck and Pokurko where they considered this random block membership case. And they compared the LDPs at scale n and scale n squared.
So this is not exactly what you talk about, but what are the main challenges if one wants to go to a bit sparser but inhomogeneous random graphs? You don't have the compactness.
I don't know. So I know that has been worked on in the Erdős setting. I'm
Right.
not sure if it has all, like the block model case has been considered in the sparse version.
I'm
Does
guessing
anyone know
not.
this?
Oh.
By Shoham and when they do the block model case, There has to be the variational problem.
That part, yeah, that part.
Yeah, but the LDP is there.
Okay, thank you.
Okay, we have more time.
Thanks for the nice talk. I just have a clarifying question about the results. So you said that the FT web, when in the symmetry case, has the same block model as the W naught. Is it also? Can you also pin down the probabilities in those blocks, or is it just?
No, we didn't like identify the solution. We just showed that it was symmetric.
Do you think?
Yeah,
it's
I don't think
hard to do?
hard to pin down a solution. If I remember correctly, it was like the solution to some like implicit function, and so I think it might be difficult to pin it down.
Thank you.
There's a question there.
Does it happen sometimes, or could it happen that you have more symmetry than in the original Graphon? I mean, if you start with a two-block model, it happens that your minimizer is a homogeneous and Erdős-Rényi graph. And will it be interesting to investigate that?
That sounds like an edge case to me, actually. Actually, I have a feeling that wouldn't really happen because you could probably lower the entropy while maintaining whatever target by kind of increasing one and decreasing the other to match the base graph.
So is there an upper bound on the number of blocks that the minimizer has as a function of the size of the subgraph whose counts you're pushing? I mean, and for that matter, is it even known that there is a finite upper bound, or are there, flipping that around, are there any natural problems where the optimizer really has some continuously varying Graphon rather than a piecewise constant one?
So we did not investigate that, but that's pretty interesting. Like if somehow the function influences the solution in terms of like finiteness or not. Yeah, I don't know. But
I think it's not even known for the Erdős-Rényi case, right? People sort of conjecture it's continuous, but nobody knows. Is that correct? Yes. I mean, maybe you have a replica symmetry-breaking solution as a physicist, but no. So I think it's not known even for Erdős-Rényi and triangles.
But I thought in some sense we saw earlier at least some regions where two blocks suffices where
Slightly different.
it's a different context, I think.
More questions? Okay, well, so we deserve tea. We'll be back in half an hour. Thank you.